Hello everyone. Today we are going to analyze a fixed beam when it carries symmetrical triangular load. In this analysis, we are going to find out the fixed end moments, reactions, and we are going to draw the shear force and bending moment diagrams. Also, finally, we are going to find the deflection in the center. First, let us find the fixed end moments. For that, we have to draw two diagrams. One is free movement diagram and another is fixed movement diagram. First, let us make the free movement diagram. For that, we have to assume this fixed beam as a simply supported beam. Then we have to draw the bending moment diagram, that is the free movement diagram. You can see that I have assumed the fixed beam as a simply supported beam. Now let us find the reactions. Here we have symmetrical loading. The reactions RA and RB will be equal to the total load divided by 2. In this triangular loading, to find out the total load, we have to find the area. We know the area formula of a triangle, half into breadth into height. Here breadth is L and height is W. So the total load is WL upon 2. To find out RA and RB, we have to divide the total load by 2. In this way, we are getting RA and RB WL upon 4. Now let us find the bending moment in the center of the beam. I am going to find out the moment in the center from the point A. In this case, I am moving towards right hand side. Clockwise will be positive and anti-clockwise will be negative. The vertical reaction RA is acting in the clockwise direction, so it will be positive and the distance is L upon 2. Then we have the triangular load. It is acting in the anti-clockwise direction, so it will be negative. For the triangular load, we have to multiply the area with the centroid distance. We know the formula for the area of a triangle, half into breadth into height. Here the breadth is L upon 2, the height is W. The centroid distance towards this height is 1 by 3 into L upon 2. L into L, we will get L square. 4 into 2, we will get 8. L into L, we will get L square. When we multiply 2 into 2 into 3 into 2, we will get 24. Here we can take LCM. 24 is the LCM. So here we have to multiply with 3 on the numerator and denominator. 3WL square minus WL square, we will get 2WL square. Then we can simplify. Here we will get 12. Finally, for the bending moment at the center, we are getting WL square upon 12. Using this value, we can make the free movement diagram. This is the free movement diagram, also known as the mu diagram. Now we have to find the area of this free movement diagram. It is very difficult to find out the area because this is a third degree parabola. In this case, we have to make integrations and find out the area. To make the integration, we have to split the beam into two parts, one on the left and one on the right. So we have to make two sections, one on the left side and one on the right side. This is a symmetrical loading. So we can make any one of the section for integration and multiply the integration with 2. By doing so, we can save a lot of time. I am going to make the section on the left side and then multiply the integration by 2. You can see that I have taken the left side and made the section at a distance of x from the point A. In this section, we have to find the moment. First of all, we have to find the intensity of the loading at the section. That means this height. We have to find out this height. For the distance L upon 2, the height is W. But I need the height at the distance of x. So we have to multiply with x. When we do so, we are getting 2wx upon L. Now let us take moment about the section. I am going to find out the moment from the point A. In this case, I am moving towards right hand side. Clockwise will be positive and anti-clockwise will be negative. The reaction in the point A is acting in the clockwise direction, so it will be positive and the distance is x. The triangular load is acting in the anti-clockwise direction, so it will be negative. For the triangular load, we have to multiply the area with the centroid distance. This is a triangle. The area formula for the triangle is half into breadth into height. Here the breadth is x, the height is 2wx upon L. Using the formula, we can find out the area. The centroid distance towards this height is 1 upon 3 into x. X into x, we will get x cube. We can eliminate this 2 and this 2. After simplifying, we will get this. We have to integrate this bending moment. The limits for the integration are 0 to L upon 2. We know that we have to multiply the integration with 2. Now let us keep W outside because it is the constant. Now let us start integration. Using this formula, we can integrate. After integrating, we are getting these. 4 into 2, we will get 8. 3 into 4, we will get 12. Then let us apply the limits. No need to apply the lower limit 0 because the whole terms will become 0. Only apply the upper limit. Instead of x, we have to apply L upon 2. L upon 2, the whole square, we will get L square upon 4. L upon 2, the whole power 4, we will get L power 4 upon 16. 8 into 4, we will get 32. 12 into 16, we will get 192. Using the calculator, we can add these two terms. When we add these two values, we will get 5L cube upon 192. Now let us cut this 2 and 192. Here we will get 96. Finally, we are getting the area of mu diagram 5WL cube upon 96. Now let us make the fixed moment diagram known as mu dash diagram. Here we have symmetrical loading. So the fixed moments MA and MB will be having the same value. The fixed moment diagram will be in the shape of a rectangle. Now let us find the area of the fixed moment diagram. For that we have to multiply MA with L. The area of mu diagram and the area of mu dash diagram will be equal. So let us equate both of them. We can eliminate this L. Here it will be square. Finally, we have made the formulas for MA and MB. We know that MA and MB will be having the same value, but they will be acting in the opposite directions. MA will be acting in the anti-clockwise direction and MB will be acting in the clockwise direction. Now let us find the vertical reactions. Here we have symmetrical loading. So same like in the simply supported beam, we can easily find out the reactions. For that we have to divide the total load by 2. In this way we are getting RA and RB as WL upon 4. Now we are going to draw the shear force diagram. Before drawing that, let us find the shear force values. I am going to find out the shear force values from the point A and towards the point B. In this case, I am moving towards right hand side. Upwards will be positive and downwards will be negative. In the point A, there is a vertical reaction. It is acting upwards, so it will be positive. Up to the point C, we have the triangular load. It is acting downwards, so it will be negative. For the triangular load, we have to find the area for the shear force. When we add these two terms, we will get 0. Now let us find the shear force at just left of B. In the point C, the shear force is 0. Then from the point C to the point B, we have the triangular loading. For the triangular loading, we have to find the area for shear force. So for the shear force at just left of B, we are getting minus WL upon 4. Using the shear force values, we can draw the shear force diagram. Now let us make the bending moment diagram. For that we have to combine the free moment diagram and the fixed moment diagram. Let us calculate the bending moment in the center. For that we have to subtract 5WL square upon 96 by WL square upon 12. When we do that, we are getting WL square upon 32. In this bending moment diagram, there are 2 points of contraflexures, one on the left side and one on the right side. We have to find any one of the distance because both of them are lying in the same distance from the ends. Let us find the distance of point of contraflexure on the left. For that we have to make one section. You can see that in the point of contraflexure I have made a section at a distance of x from the point A. In the section we have to find the intensity of the load, that is the height at the distance of x. In this analysis previously we have already found one term for the height 2wx upon L. We can use the same here. No need to find again and again. Let us take moment about the section. MA is acting in the anti-clockwise direction, so it will be negative. The vertical reaction is acting in the clockwise direction, so it will be positive and the distance is x. The triangular load is acting in the anti-clockwise direction, so it will be negative. For this triangle, we have to multiply the area with the centroid distance. This is the area and this is the centroid distance. We know that in the point of contraflexure, the moment will be 0. After simplifying this, we are getting this. From these three terms, we can take W outside and let us take W on the right side. 0 by W, we will get 0. For these three terms, let us keep 96 as common. We have to multiply this term with 24 on the numerator and denominator. We have to multiply this term with 32 on the numerator and denominator. then we will get 96 as common. Let us take 96 outside and take on the right side. 96 into 0, we will get 0. Then we have to solve this equation. It is very difficult to solve this equation. So let us apply x is KL. In this equation, instead of x, we have to apply KL. We can eliminate this L and here it will be square. Now L square is common. Let us take it outside and bring it on the right side. 0 by L square, we will get 0. Then let us take minus 5 on the right side. It will become positive. Now using trial and error method, we can solve this equation. After solving, we are getting K. We know that x is KL. Here instead of K, let us apply 0.223. Using the calculator also, we can solve this equation. Now you can see the bending moment diagram with the distance of point of contraflexures. In the fixed supports, there will be no slope. So in the points A and B, there will be no slope. In this case, theta A and theta B are 0. Also, in the fixed supports, there will be no deflection. So YA and YB are 0. Now, let us find the deflection in the center, that is the point C. For that, we have to make a section in this beam. This beam has symmetrical loading, so only one section is enough. I have made the section randomly here at the distance of x from the point A. We know that the intensity of the load in the distance of x is 2Wx upon L. Now let us find the moment in the section. MA is acting in the anticlockwise direction, so it will be negative. The vertical reaction is acting in the clockwise direction, so it will be positive and the distance is x. The triangular loading is acting in the anticlockwise direction, so it will be negative. For the triangular loading, we have to multiply the area with the centroid distance. Let us equate mxx with EA d square y upon dx square. Now let us integrate on both of the sides. When we integrate EA d square y upon dx square, we will get EA dy upon dx. For integrating the right side, we can use the formula. After integrating, we will get this. 4 into 2, we will get 8. 3 into 4, we will get 12. C1 is the constant. This is the equation for the slope. Now let us integrate the slope equation. When we integrate, we will get this. C2 is the new constant. 96 into 2, we will get 192. 8 into 3, we will get 24. 12 into 5, we will get 60. In the point A, there is a fixed support. In the fixed support, there will be no slope. So when x is 0, dy upon dx will be 0. In this equation, let us apply x is 0 and dy upon dx is 0. When we do that, we are getting C1, which is equal to 0. In the fixed support, there will be no deflection. So when x is 0, y is 0. In this equation, let us apply C1 is 0, x is 0 and y is 0. When we do that, we are getting C2, which is also 0. In the EIY equation, let us apply the values of C1 and C2. When we do that, we are getting this. Now let us find the deflection in the center. In the center, the value of x is L upon 2. So in this equation, instead of x, we have to apply L upon 2. We can use the calculator and simplify. Finally, for YC, we are getting minus 7 WL power 4 upon 3840 EI. We got a negative value, that means it is the downward deflection. Now let us compare the deflection value with a simply supported beam having the same symmetrical triangular loading. For the simply supported beam, YC is WL power 4 upon 120 EI. For the fixed beam, YC is 7 WL power 4 upon 3840 EI. So YC of fixed beam is 7 upon 32 of YC of simply supported beam. Now we are going to end this session. Thank you for watching this video.